Yes, welcome to this session on second law of thermodynamics. Here we will discuss the questions from assignment number 2, which is based on second law of thermodynamics. Here we will do some quick revision of important formulas and then we will discuss the questions. Okay, so come to next slide. So first we have heat engine. First we have heat engine. In heat engine we have a thermal energy reservoir at higher temperature, and if we get heat into heat engine, this is heat engine, and we get this heat to a lower temperature, this is TL, and in heat engine we will get some work output. This is our system. Okay, so this is thermal energy reservoir, its temperature will remain constant, and we will get Q1 heat from this TH, and we will receive Q2 heat to this TL. Okay, so I am taking this TH as T1, TL as T2. Okay, whenever I get any system like this, right, for this heat engine or refrigerator, so first equation which will come into our mind, this is what conservation of energy. So if this is our system, so what is going to happen here? Q1 is energy in equals to Q2 plus W. This is one equation, energy balance. And if I write thermal efficiency of this heat engine, this will be what? W, work done, upon Q in. So this will be what? If I take W from here, it will be Q1 minus Q2 upon Q1. So we will get 1 minus Q2 by Q1. Okay, and if this heat engine is reversible in nature, then we can write 1 minus Q2 by Q1 will be equals to what? T2 by T1. Okay, so here we get, for reversible heat engine, Q2 by Q1 is equals to T2 by T1. Okay, so these are the important formula for heat engine efficiency, and how heat and temperature is related for reversible heat engine. And okay, one important point here, T2 and T1 will be in Kelvin. It will be in Kelvin, not in degree Celsius. ठीक है, अदरवाइज आपके आंसर गलत आएंगे. So this is for heat engine. Let's go to next slide. So similar concept we have for refrigerator. In refrigerator we have surrounding higher temperature, so this will be TH. This cycle direction will be reverse, so this is refrigeration cycle, and here we will have TL. So heat will come from, so what we are doing here, we are extracting heat from this lower temperature system. So we write this as Q2 and we write this as a Q1. on refrigeration, there will be work done on the refrigeration. So this is the standard setup for refrigerator. Refrigerator is a device which maintain lower temperature comparison to surrounding. Okay, and now some important point with respect to refrigerator is, first we will write energy conservation for this system. So you can see in this system what is the energy input. This is q2 plus w equals to energy out. This is what q1. Okay, this is one relation. And if I write COP, coefficient of performance, this is what desired effect upon work input. So if I write COP for heat pump, so in heat pump our desired effect will be what? Q1 upon W. So this will be Q1 and W will be what? W value will be Q1 minus Q2. This is a COP for heat pump. And if I write COP for refrigerator, this will be in refrigerator. Our desired effect is what? Just we want to reduce the temperature of a room, and we want to reduce the temperature, we want to keep the temperature of the room up to TL, and by doing this we have to extract the Q2 heat. So Q2 will be the desired effect. This will be what? Q2 upon W. So this will be Q2 upon W value will be what? Q1 minus Q2. And from these two relation, coefficient of performance for heat pump and coefficient of performance for refrigerator, we will get one relation. Just subtract these two equation, we will get coefficient of heat pump equals to 1 plus coefficient of performance for refrigeration. So this is the standard relation for coefficient of performance for refrigerator and heat pump. So this is important for refrigerator, right? Okay, and in case of reversible refrigeration cycle, we will get COP of heat pump will be what? Q1 upon Q1 minus Q2, and this we can write T1. So I am taking this as a T1 and this as a T2. T1 upon T1 minus T2. Okay, and COP of refrigeration will be how much? Q2 upon Q1 minus Q2. This will be T2 upon T1 minus T2. In our syllabus only this reversible cycles are there, so we can use this relation. Okay, and one important point comes, Clausius inequality. So here it tells three conditions. So first relation is del q by t. In cyclic integral of del q upon t is 0 for reversible cycle. And integral del q upon t is less than 0 for irreversible cycle. and integral del q upon t is greater than 0 for impossible cycle. So these are the some important concepts from second law of thermodynamics. Now let's move to next slide. Okay, so this is explain the heat engine, refrigerator and heat pump with neat sketch. I hope ये सब आप कर लोगे. ओके अच्छा यहाँ पे okay, come to next question. State and explain equivalence between Kelvin Planck and Clausius statement of second law of thermodynamics. Okay, fine. Okay, अपन यहीं पे ड्रॉ करते हैं. So let's try to understand this. Okay, fine. So here first just I am explaining you what is Kelvin Planck statement. What is Kelvin Planck statement? This is what state and explain equivalence between Kelvin Planck and Clausius statement of second law of thermodynamics. So first let's understand what is Kelvin Planck statement. So this statement is only valid for a cycle. So what it says, if we have a thermal reservoir at T1 and it is receiving heat engine is here and we are getting work directly. Okay, this is Q1 and here Q2 is 0. So it says it is impossible for a device to develop a device operating on a cycle which produces work continuously while exchanging heat with a single reservoir. So this is impossible to achieve. What it says that Q2 will be 0 here in Kelvin Planck statement. So if I write the energy conservation, it will be Q1 equals to W, and if I take efficiency, this will be what? W upon Q1. So this will be what? 1, and in this we will get efficiency value as 100%. So it means in any cycle efficiency cannot be 100%. So this is Kelvin Planck statement, right? Okay, similarly we have Clausius statement. Similarly we have Clausius Clausius statement. Clausius statement, this is for refrigerator. So what it says, this is we have TH and here we have refrigerator cycle and here we have TL. So it says that it is impossible to develop a device operating on a cycle and which transfer heat from lower temperature. Let's take this T1, T2, this is Q2, this is Q1, from lower temperature to higher temperature without any work input. So this will be 0. So this is the statement for this is the Clausius statement, right? So okay, and these devices are impossible to develop. Okay, so another important point is equivalence of Kelvin Planck and Clausius statement. Now let's try to understand this. What is this concept? So first make first make a cycle. This is at higher temperature, and here we have heat pump, and here we have lower temperature, and here we have heat engine which work from higher temperature to lower temperature, and it is producing work. This is Q1, this is let's take this Q2, and on heat pump it is Q3, this is Q3, and this is Q1, Q2, Q3, and this is what, Q4. Okay, so this statement is, now here what is happening in this statement, we have violation of Clausius statement. So what is happening here, we are transferring heat from lower temperature to higher temperature without any work input. So here work input is 0. Okay, so what is going to happen here? So now here if I write the energy balance, so you can see that Q3 equals to Q4 because there is no work done, and here and this Q4 will be equals to Q1 because we are extracting same heat from the hot reservoir. So I hope it will be clear to you that if this condition is fulfilled, then we will get something like this. So this will be lower temperature thermal reservoir, and this heat will go here in heat pump, and it will directly come to heat engine, and this Q2 will be delivered to lower temperature, and we will get W. Okay, W as Q1 minus Q2. So here you can see, here we will get Q1, here we will get Q1, and this Q1 will come into this heat engine from this relation. So if I make this as a system, so you can see here this heat engine is producing this amount of work with exchanging heat only with a single thermal reservoir. So this is what violation of Kelvin-Planck statement. So this is what violation of Kelvin-Planck statement. So the vice versa is true for, so here we have taken initially that this, if this machine, this cycle is violating the Clausius statement, so we get that if cycle is violating the Clausius statement, we will get violation of Kelvin-Planck, and similarly vice versa, if cycle will violate Kelvin-Planck statement, it will violate the Clausius statement. So let's try to explore the next part. I am doing it here. Okay, so now if it is violating the violation of Kelvin-Planck statement. Okay, so what is happening here? So here we have higher temperature reservoir, T higher, and here we have lower temperature reservoir, this is TL. Okay, and what is happening here? It is extracting Q1 amount of heat. This is heat engine, and here Q2 is 0, and this is Q2 is 0, and this is producing work that will be equals to Q1, and this work is going as an inlet, going as an input to the heat pump which is supplying heat Q1 to higher temperature reservoir, and it is extracting Q2 heat from the lower thermal reservoir. Now if we see this heat engine is violating the Kelvin Planck statement, and from here if we write the energy balance for heat pump, we will get this is Q1, this is Q2, okay, and we can just write it as Q3. Okay, so from here I hope we will get Q3 equals to W plus Q2, W plus Q2, and W value, and W is equals to Q1. So here we will get W equals to Q1 plus Q2. Now if I make one final cycle, one combined cycle, so this is combined cycle, right? So here we have lower temperature, this is at higher temperature, so this is what combined cycle, right? So you can see here this combined cycle is taking Q2 heat from TL, and it is taking Q2 heat from TL, and if you see here Q1 plus Q2, Q1 plus Q2, it is rejecting to TH, and here it is gaining Q1, so net heat will be what? Q2. Okay, now you can see here now you can see here that this combined cycle is transferring heat from lower temperature to higher temperature without any work input. So this is what violation of Kelvin Planck statement, right? So we have seen that if Kelvin Planck statement is violated, then we will get the violation of class S statement, right? So this is violation of class S statement. W is 0, and we are transferring heat from lower temperature to higher temperature. So this is what equivalence of Kelvin Planck and class S statement. Okay, so let's go ahead. So this is question number 3. Question number 3. Three Carnot engines are arranged in series. The first engine take. So here we have this is T1, this is heat engine 1. Three Carnot engine are arranged in series. So this is one engine, this is T2, this is E1, E2, T3, let me draw it. Let me draw it here. This is T1. So three Carnot engines are arranged in series. Okay, so we will make E1, this is T2, this is E2, this is T3, this is E4, this is T4, so three Carnot engine are arranged in series. The first engine take, this is Q1 is 4000 kilojoule of heat from a source of T1 is given as 2000 Kelvin, and delivers 1800 kilojoule of work. So W1 is 1800 kilojoule. the second and third engine delivers. Okay, so it is given W2. W2 is how much? 1200 kilojoule. And this is engine 2, this is engine 3. Third engine is delivering 500 kilojoule. Determine the exhaust temperature from second. So from second and third engine, from second, this is third and second, so we want T3 and T4. Okay, so as we have learned earlier, the first write what the quantity they have given, we have already written. Then for heat engine 1, now if we focus heat engine 1, just write the energy balance equation. Now this is Q1, let's write it Q2. We can write, if I take heat engine as a system, so Q1 will be equals to W1 plus Q2. So I hope we will get Q2 value here. We will get Q2 value here. It will be how much? 4000 minus 1800. We will get 220 kilojoule. Okay, now apply the formula for efficiency of heat engine 1. What we get, as we have discussed earlier, the formula was W1 upon Q1. Okay, so W1 value, W1 upon Q1, or we can write 1 minus Q2 upon Q1 equals to 1 minus T2 by T1. Okay, so we have Q1 value, we already have, it is 1800, and this is W1 value, and Q1 is how much? 4000, and we have T1 value, we already have here. So you just put in this relation, and we will get T2 value as 1100 Kelvin. This is for heat engine 1. Now we get the T2 value. Now again write for heat engine 2. Now let's focus on this heat engine. This is Q2. Now let's write this heat as Q3 and this heat as Q4. We can write by energy balance, we will get so here Q2 will be equals to Q3, right? Q2 will be equals to Q3. So just write this name. This will be what? Q2. This will be Q3. Okay, so from here we can write, from energy balance, we can write Q2 equals to Q3 plus W. Okay, so from here can we get Q3 value? Now just do this calculation. We have W2, this is W2 value, we already given here, we know Q2 value. Now just calculate Q3 value, we will get 1000 kilojoule. Now write efficiency for heat engine 2. This will be W2 upon Q2, W2 upon Q2, and this will be what? This will be 1 minus Q3 upon Q2, or 1 minus T3 upon T2. This will be equals to W2 upon Q2. So W2 we have 1200 upon Q2. Q2 is how much? Q2 is how much? Is 220. And we have T2 value, we already calculated. Now just calculate the value of T3 from here. calculate the value of T3 from here, we will get T3 as 502 Kelvin. T3 as 502 Kelvin. So this is the temperature T3. Now come to engine 4. So this will be Q3 and this will be Q4, right? Engine 3. For engine 3, now write the heat balance equation, energy balance equation. It will be Q3 equals to Q4 plus W3. So from here can we get the W value of Q4, because we already calculated Q3 is here. So can I get Q4? Q4 will be, just do this calculation, we will get 500 kilojoule. This is Q4. Now write the efficiency formula for heat engine 3. This will be how much? W3 upon Q3, or we can write 1 minus Q4 upon Q3, or 1 minus T4 upon T3. This will be equals to 500 upon Q3. Q3 is how much? 1000, right? So we have T3 value from here. Just calculate T4 value. T4 is how much? 251 Kelvin. So I think determine the exhaust temperature from second and third engine. So we have calculated all the values here. Now come to next question. This is question number 4. Now a heat pump working on Carnot cycle takes in heat from reservoir 5 degrees Celsius and deliver heat to a reservoir at 60 degrees Celsius. Okay, so let's try to draw this. So we have a heat pump working on Carnot cycle take heat from a reservoir. So this is heat pump. So this is what this is TL, this is heat pump, this is TH, higher temperature. Okay, heat pump working on Carnot cycle take heat from the reservoir at 5 degrees Celsius. So this is, let's take this T1 is 5 degrees Celsius and deliver heat to a reservoir at 60 degrees Celsius. So let's take this as T2 is 60 degrees Celsius. The heat pump is driven by a reversible heat engine which takes heat from a reservoir. Now this is driven by a heat engine. The heat pump is driven by a reversible heat engine. So right, this is what Carnot cycle is a reversible cycle, right? So here, now this is what driven by heat pump is driven by a heat engine which takes in heat from a reservoir. So this is T3 it is given 840 degrees Celsius, and this is what heat engine from reservoir at 840 degrees Celsius and reject heat to a reservoir, and this is rejecting heat to a reservoir which is at T4, and T4 is given as 60 degrees Celsius. The reversible heat engine also drives a machine that absorbs 30 kilowatt. So and reject heat to reservoir. The reversible heat engine also drives a machine. So this will be what? Some portion will go in doing W1. Now let's take W1 work is for driving the heat pump, and W2 work is for 30 kilowatt for driving another machine. Okay, if the heat pump extract uh, this amount of heat from 5-degree reservoir, so this is what Q1, this is Q2. So Q1 is given as 17 kilojoule per second. सो यूनिट यहाँ पे ध्यान में रखना है, Q1 वैल्यू इज़ 17 किलोजूल पर सेकेंड फ्रॉम 5 डिग्री सेल्सियस रिजर्वायर. ओके, आई थिंक यहाँ नाउ एवरीथिंग इज़ क्लियर अप टू दिस. सो नाउ determine the rate of heat supply from 840 degree Celsius source. We have to calculate this Q3, the rate of heat rejection to 60 degree Celsius sink. So this is Q4. These two quantities we have to calculate. Now let's try to analyze this problem. Now let's write COP for heat pump. This will be what desired effect upon work input. So this will be what Q2 upon W1, or we can write it, this will be Q2 upon, so if I write the energy balance equation for heat pump, this will be what Q2 equals to W1 plus Q1. This should be clear. So from here, if I take W1, it will be Q2 minus Q1. Okay, so can I write this in terms of TH upon TH minus TL. Okay, so I hope we have all the values. TH value is 60 degrees Celsius. Now here you have to put TH value, put all the values in Kelvin. So TH will be 60 plus 273, and this will be here, actually this is the difference. So if we will add 273 on both sides, it will be subtracted. So just do simply 60 minus 5. Okay, just do this calculation, we will get 6.05. This will be COP of heat pump. Okay, this will be COP of heat pump. And sorry yaar. So you can see from here, so I have written the coefficient of performance for refrigerator. So this will be desired effect upon W1. So from here we did this and we obtained the COP of refrigerator here. So from COP of heat pump and refrigerator, you can see if we add 1 in coefficient of performance for refrigerator, we will get this value. And from here we calculated the W1 value, and from here we calculated the Q2 value. So this is what Q2 value for this relation for heat pump. Now I'm just removing this section. Okay, fine. Now let's focus on heat engine. If we write efficiency of heat engine, this will be efficiency of heat engine. This will be 1 minus T lower upon T higher. So this is 1 minus T lower is how much here? This is 60 plus 273 upon T higher is 840 plus 273. Okay, so just do this calculation. We will get efficiency value is 0.701. Okay, this is what efficiency for heat engine, and this we can equate. It will be equals to work total upon work total upon Q3, work total upon heat input, that will be what? Q3. Okay, so work total, how we can calculate work total? So you can see work total will be W1 plus W2. W1 we have calculated from here. This is the work required to run the heat pump. This is 3.36 plus 30 we will get 33.36 kilojoule per second. Okay, this is given in kilowatt. किलोवाट का मतलब क्या होगा? किलो जूल पर सेकेंड. ओके, और 33.36 किलोवाट. Okay, so this is what W total, and from here we get, I think, W total value we get. Now put the W total value here. We will get Q3 value. So Q3 will be how much here? Q3 will be W total upon 0.701. So now do this calculation. So W total is 33.36 divided by 0.701. So we will get Q3 as 47.58 kilowatt. Okay, now just write the energy conservation for this heat engine. We can write Q3 is equals to W total plus Q4, right? Or Q4 is equals to Q3 minus W total. So just put, we have Q3 value, we have calculated Q3 value, we know W total. Just do this calculation. Q3 is how much? 47.58 minus 33.36. We will get 14.22. So this is, I think, we got Q4 and Q2. This was the question to calculate the Q2 and Q4 values. Now let's move to the next question. Okay, question number 4, question number 5. A reversible heat engine here we have one reversible heat engine. So here we have this TH, TL, this is heat engine, operates between two reservoirs at temperature of 7. This is what I am taking TH as 700 degrees Celsius and TL as T2 as 50 degrees Celsius. Okay, the engine drives a reversible refrigerator which operates between, so here this is refrigerator cycle which operates between reservoir at temperature of, so here T1 T2, I am taking this lower, this will be lower temperature, this is T3, and T3 is how much, minus 25 degrees Celsius, and this is T4. T4 is how much, 50 degrees Celsius. The heat transfer to the engine is 2500 kilojoule, and the net work output of the combined engine refrigerator plant is 400 kilojoule. So here it is given, this is Q1 is given, the heat transfer to the engine is 2500, this is 2500 kilojoule, and the net work output of the combined engine refrigerator plant is, so here, so guys, what is going to happen, this will be like this. Okay, so what is happening, some work will come from engine to refrigerator. I am writing it like this. This is work done on the refrigerator cycle, so this is what WE. Now what it is saying, the W net, the net work output of the combined engine refrigerator plant is 400 kilojoule. So what W net it is giving, work done by the engine minus work consumed during the refrigeration cycle. This is how much, this is 400 kilojoule, this is 400 kilojoule. Now determine the heat transfer to the refrigerant and the net heat transfer to the reservoir at 50 degrees Celsius. So this is what Q1, this is Q2, this is Q3, this is Q4. Determine the heat transfer to the refrigerant and the net heat transfer to the reservoir at 50 degrees Celsius. So here it is asking heat transfer to the refrigerator. This is refrigerator. So this is asking to this Q3 value, and heat transfer to the reservoir at 50 degrees Celsius. It is asking to calculate Q3 and Q4. Okay, so let's write the energy conservation equation for this heat engine. For heat engine, so this will be Q1 plus W from heat engine plus Q2. Okay, so here W net is given as 400 kilojoule. So this will be what work done by the heat engine, and this will be work done on the refrigerator. Okay, so we have taken this negative sign to show that work done is on the system. Okay, that's why we have taken this negative sign here. Okay, so efficiency for this heat engine will be eta equals to this will be what WE upon Q1, or we can write this will be what Q2 minus Q1, this will be what WE will be Q1 minus Q2 upon Q1. So this will be, for reversible engine we can write, this will be 1 minus Q2 by Q1. So efficiency will be 1 minus T2 by T1, right? So we have this T2 and T1 we have, so just write the values. 1 minus T2 is 50 degrees Celsius, 50 at 273 here, we will get 323 upon T1 is 973 is equals to 0.668. This is the efficiency for a heat engine. Efficiency for heat engine. Now calculate WE value. This will be how much? Q1 into eta. So we have Q1 already we have given, so just multiply it by efficiency. This will be multiplied by Q1 is 2500 kilojoule. Okay, so this will be how much? 1670 kilojoule. Okay, this is what work done. This is the maximum work done from the heat engine. Okay, now we know that W net is WE minus WR equals to 400. So from here, can you tell me what will be the value of WR? I think we have WE, we have just calculated that. Calculate the value of WR, we will get 1270 kilojoule. Okay, so this is what WR we have calculated from here. Now we have this T3 we have given and T4 we have given. जब भी whenever we have the temperature of cold sink and temperature of hot sink, of temperature of these two sinks are given, so सीधे दिमाग में ये स्ट्राइक करना चाहिए कि हमें अभी अगर हीट इंजन दिया है तो वहाँ पे इफ़िशेंसी का फार्मूला लगाएंगे, अगर हीट पंप या रेफ्रिजरेटर दिया है वहाँ अपन COP का फार्मूला लगाएंगे. सो दिस विल बी व्हाट? COP. So just calculate COP for refrigerator. This will be how much? This will be T3 upon, this will be T3 upon, so just write it properly, we will get the answer. So this will be what? Q3 desired effect upon WR. Okay, and just write the energy balance for this heat, the refrigerator. We will have WR plus Q3 equals to Q4. Okay, so put the value of WR in this, we will get, this will be equals to Q3 upon WR will be what? Q4 minus Q3. Okay, so for reversible refrigerator cycle, this will be T3 upon T4 minus T3. This will be this. So just write the values. We will get 240. Just add, this is T3, we write minus 25 plus add 273. This is T3, and here T4 is how much? Add 50 plus 273 and just subtract this value. We will get 323 minus 248. So we will get COP of refrigerator as 3.30. Okay, so this will be COP of refrigerator, and we want to calculate this Q3 will be what? COP of refrigerator into WR. Okay, so we have WR given, we calculated from this relation, and COP is this, then multiply it. WR is 1270 kilojoule, so we will get 4190 kilojoule. Okay, so this is the value of q3. Now if I want to calculate q4, how we will calculate? uh, we want to calculate q4. Now so here we get q3 value, and now we have to calculate the value of q4. So can we get from the q4 value from this relation? Okay, so to do this calculation we will do uh, q4 will be wr plus q3. So wr is 1270, and q3 is 4190. We will get 5460. Okay, so this is the q4 value for kilojoule. Now it is asking, determine the heat transfer to the refrigerator and net heat transfer to the reservoir at 50 degrees Celsius. So 50 degrees Celsius पे यहाँ पे we have two reservoir. One is this T4 and one is this at T2. Then total heat required for 50 degrees Celsius reservoir Q50 will be how much? Q4 plus Q4 plus Q2. So Q4 we have calculated from this relation, and Q2 you can calculate from this relation. From this relation you can calculate Q2 value and just add these two values. So we will get the final answer. So right, this is the solution for part 1. Now part 2, what it is saying, if efficiency, reconsider one, given that efficiency of the heat engine and the COP of the refrigerator are each 45% of their maximum possible value. So okay, now I am just removing this. In this case what it is saying, that consider one, given that efficiency of the heat engine and COP of the refrigerator are each 45% of their maximum possible value, right? So this is what, so this will be eta will be equals to 0.45. we have calculated eta earlier, that was 0.668. so we will get eta value as 0.306. okay, and just do the calculation for COP of refrigerator. It will be 0.45 of existing COP. So this was 3.30. We will get 1.49. So now again what we have to calculate, we have to calculate work, calculate the work transfer from this was WE, this was WR. So this will be what? 0.306 into Q1. Q1 was this, so we will get answer as 751 kilojoule. Okay, and for refrigerator work we know that net work was 400, so refrigerator work will be WE minus 400, so this will be 341 kilojoule. Okay, and heat transfer to refrigerator, so we will get this Q3 will be 1.49 multiply 351, we will get 523 kilojoule, right? So similarly we have to write the equation for energy balance and calculate Q4 and Q2 value and add this. So Q50 reservoir, we will add Q2 plus Q4, you will get the final answer. So this is all for this question. So let's move to the another question. So I think this is the last question. A reversible heat pump is used to maintain temperature of 0 degrees Celsius. A reversible heat pump is used to maintain temperature of 0 degrees Celsius. Okay, so here it is, this is TL. When it rejects the heat to the surrounding at 25 degrees Celsius, so this is TH, this is, I am taking this T2, this is 25 degrees Celsius. If the heat removal, so okay, if the heat removal rate from the refrigerator is, okay, so it is Q1, this is Q2. If the heat removal rate from the refrigerator is, so this is Q1 is given, it is given as 1440 kilojoule per minute. Okay, determine the COP of the machine and the work input required. So this will be work. Okay, now let's try to T1 is 0 degrees Celsius. So I hope we have all the values here, right? So let's try to COP of the machine, and this is written for heat pump. Now first calculate COP of heat pump. So how we define COP? COP is defined as desired effect. So what is for heat pump? In case of heat pump, we want to maintain the room temperature at this 25 degrees Celsius, right? So this Q2 will be the desired effect, Q2 upon work input. Okay, and if I write the energy conservation equation for this as a system, this is heat pump. If we write energy conservation equation, what we will get? We will get Q2 equals to W plus Q1. Okay, so from here we will get W equals Q2 upon W. W will be Q2 minus Q1, or we can write, see here temperature is given, so this will be what, T2 upon T2 minus T1. This is for reversible heat pump, right? सो जहाँ पे टेम्परेचर दिए रहे हैं एंड कंडीशन पे दिमाग में ये स्ट्राइक करना चाहिए, COP लगाना है, दैट्स इट. सो यू जस्ट राइट ऑल द वैल्यूज़ हियर. सो हियर वी विल गेट 298 upon 298 minus 273. This we will get 11.92. Okay, run COP and the machine work input. So this we get, and we have Q1 value. Q1 value is given. Q1 value is already given. Okay, if Q1 is given, so can you tell me Q1 is given, just apply the energy balance relation. Can we calculate Q2 value? So Q2 will be how much? Q2 will be W plus Q1 is 1440. Unit is kilojoule per minute. This is Q2 value. Now use this relation. COP is 11.92. Q2 is how much? W plus 1440 upon W. Now solve this relation. Now solve this relation. We will get W as 2.19 kilojoule per second. So guys, we have taken Q1 as kilojoule per minute. So what you do, divide it by 60, we will get 25 kilojoule per second, right? So this will be what W unit will be 2.19 kilojoule per second, right? I think we have calculated all the things. Determine COP of the machine and work input required. Okay, so this we have calculated. If the required input, now second question, now if the required input to run the pump is developed by a reversible engine, if the required input to run the pump is developed by reversible engine which receives heat as 380 degrees Celsius and reject heat to atmosphere, then determine the overall COP of the system. Okay, so here what is happening, that reversible engine will driving the heat pump. So I'm just writing it here. So this is similar to previous question. So here we have engine source at which receives heat at 380 degrees Celsius and reject heat to atmosphere. So that TH will be 380 degrees Celsius and it will be rejecting heat to TL to atmosphere. Atmosphere means just take this 23 degrees Celsius. Okay, just add 273 in this. Okay, so this will be in Kelvin. Add 273 in this for your calculation. Okay, and reject the heat to atmosphere. Then determine the overall COP of the system. Overall COP of the system. Okay, so this is the scene. This is TH. This is heat engine. Okay, this is driving heat pump. This is TL from refrigerator. This is refrigerator. This is TL. This is TL. So what is going to happen here? This is similar. Just write the energy balance at for this, write the efficiency for this, write COP for this, and you can calculate all the values. So overall COP, this is asking overall COP, over determine the overall COP of the system, right? So you can, if I take this as Q1, Q2, Q3, Q4. Okay, so just I think you can do all the calculation. So we have, so you can calculate the COP of the system. So here if we write overall COP, we will get this Q3 upon Q1. Okay, so just you can calculate from here. So we will get Q3 upon, this will be W upon eta, and Q3 upon W will be what? COP of refrigerator into eta. So the final answer you will get at 6.48. This is the overall efficiency of the cycle. So I hope this is all, and remaining question, these questions are from your booklet, from your handwritten notes, so you can check this question from there. This is I think so this is from I think process inequality. Okay, these are from your handwritten notes, so you can go through from there. Okay, so this is all for today.